Hi, so in the last set of lectures that we had, we looked at linear secret sharing schemes and how you construct these, how they allow for linear operations, and how you check when you get some shares whether they're consistent or not. So we kind of assume that you've already seen that, so have a look back at that. What we're going to do in this set of lectures is actually how we take those basic linear secret sharing scheme components and how we allow them to compute an arbitrary function. Okay, so that's what we're going to do today. And what we did last time is we looked at Q2 access structures and we looked at full threshold access structures. And it turns out that there's very different protocols for doing Q2 and full threshold. And what we do is we are going to look at protocols which work in a kind of three phases. The first phase is what's called preprocessing, where you produce some what are called so-called multiplication triples. Then there's a different method for Q2 and full threshold. Then we do a form of sacrificing, and then at the very end we're going to look at how you actually do the online phase, which is actually compute the arbitrary function. So at the moment we're still really not actually at the point of computing a function, but the first thing we're going to do is look at Q2 access structures and how we do this form of preprocessing. So what is preprocessing? Well, the goal of preprocessing is to produce a large number of shares of things of a special form. And the preprocessing doesn't depend on what actual function we're actually going to compute, so that's fine. But we're going to kind of fix things, we're going to use this angle bracket notation to produce what we call these authenticated shares. So shares that we can detect when they're open to us, whether they're valid or not. Okay. So what we're going to do is going to give you two methodologies. One which is what's called malware preprocessing for Q2 access structures, and then a method that's actually based on somewhat homomorphic encryption for full threshold access structures. And the system that we produced in Leuven called Scale actually contains another method for Q2, but we're going to ignore it in these notes because that's just a little bit more complicated. But you can read about that later. So what are we trying to do in preprocessing? Well, we're actually trying to produce four types of data. We're trying to produce what are called multiplication triples, which are a random sharing of a random value A, a random value B, and the sharing of its product, of this product of A and B, which we'll call C. Okay. So the A and B are random, but A, B, and C are unknown by any non-qualified set of players. We also want to produce square pairs and random shares. So a random share is a sharing of a random bit in 0, 1. Okay, now the reason we want to produce these two is not because it allows us to compute more functions, it's just it allows us to compute functions more efficiently. So you can kind of think about, if you just want to keep it to the simplest, more theoretical way of looking at MPC, then you could just think of just computing multiplication triples. But what you do need to compute to be able to input values is what these input tuples, which is basically for every player I, you need a sharing of a random value where the value R is known to the player I. So that's kind of what we need to also produce if we're going to allow players to input and output values. But okay, so how are we going to do this? Well, for Q2 access structures, we're actually going to use what's called the first component we're going to use is something called a pseudorandom secret sharing. And so we're going to do this in two ways. Now, if the number of maximally unqualified sets is large for the Q2 access structure, so for example, if we have a threshold structure with n equals, 100 and the threshold t being 50, then the number of maximum unqualified sets is huge. Okay, so if we have that case, what we can do is to produce a random sharing of a value r, we can actually do it by interaction. We can basically, everybody generates a sharing, distributes their shares to everybody, and then we just add them up. Okay, and this will produce a random sharing of a random value. Okay. Now, if a player shares incorrectly, we're going to know this later on when we apply the error detection capability of Q2 sharing. So we don't really care about whether we can verify that the guy is honestly sharing, because we're just going to abort anyway if something goes wrong. Okay, so that's what happens if we've got a large number of maximally unqualified sets. but it requires interaction. Now, if we have a smaller number of maximally unqualified sets, which usually happens because we're usually talking about a small number of parties, like we're talking n equals 3, t equals 1, or n equals 4 with some weird access structure, then we can actually do this thing without interaction, and that's really kind of cool, because interaction is what costs us time. So the way we do this is we're going to use a bunch of PRFs, which are going to be here. They're going to take a key, which is going to depend on something, which we'll come on to that something later. Some value A, and then produce an element in the finite field. And this is going to be a pseudo-random function. So just imagine this is instantiated with like an AES PRF or something. Okay, now where are these sets A's coming from? These sets A's which define these keys here. Okay, so what they're going to do is for every subset of, if we take the threshold, a Shamir sharing, for every subset of size n minus t, okay, we're going to define a polynomial. And this polynomial is going to be 1, have value 1 at position 0, and have value 0 for all I not in the set, okay? So it's of degree t, so here we have, this is going to have t plus 1 constraints. This gives us t plus 1 constraints. A polynomial of degree t has t plus 1 coefficients. So this uniquely defines a polynomial for this set of size n minus t. And then for each one of these sets A, what we do is we define a key to the PRF which depends on this set A, and we give that key to every party in A. Now the way to do that is we can just for every one of these subsets A, we can generate a key just by randomly sharing stuff and adding it together, okay, with commitments obviously. Okay, and so so here we see why we need to keep the set of maximally unqualified sets small, because if we have a large number of maximally unqualified sets for this threshold structure, then basically the number of these keys we have to define becomes exponentially large. So if the number of these keys is small, then this is kind of doable. Small could be less than 50, say. I mean, this is kind of, or less than 100. So we're not really, it's small, but not too small. Okay. And then we can generate a Shamir sharing by just non-interactively, very quickly. So all parties, what they do is to generate a Shamir sharing is that they select the next value A in this set S, so they just maybe keep a counter going, and they apply the PRF to their key, and then they sum up all of the shares I and A, because these are all the ones they know, and if they don't know the value, if they don't know the key KA, then we've already set this FA of 0. So if you don't know the key, then your bit has no contribution. So this gives us the sharing very easily. Okay, so these are the shares. So what's the underlying polynomial for Shamir? Well, the underlying polynomial for Shamir is exactly this polynomial here, and the underlying secret is this polynomial. And so what we can see is that this is just with just a click of the button, we can generate a random sharing really fast. So this is super fast, super good, and that's how it works for Shamir sharing. And you can generalize it to any Q2 linear secret sharing scheme as follows. You basically, for every set A, which is the complement of a maximally unqualified set, we can find a sharing of 1. What's this sharing of 1? Well, this sharing of 1 corresponded to this. This was the sharing of 1 for every maximally unqualified set, which has 0 contribution from all parties in P minus A. This is always possible, so this is the analog for the Shamir sharing here. And then for every one of those sets, we distribute a key to each player, and then we just go as we did for Shamir. So this generalizes as long as the number of maximally unqualified sets is not too big, which in general it can be exponentially large, so we can't use this in general. But for small values of n, this is fine. Okay. So how do we do this for a general access structure? Okay, so we have these sharings of 1, which are 0, all these things not in A. We just apply the same thing. The underlying secret is that, and everything is just the same. It's just mapping from Shamir to a general access structure. Very, very simple. Okay, so how are we going to represent this in our protocols? What we're going to do is we're going to say this thing is a pseudo-random secret sharing. So, and we're going to represent it by a function, PRSS, which just gives us a random sharing of A. Now, if the underlying access structure has a large number of maximally unqualified sets, then this PRSS is a protocol. And if it has a small number of maximum unqualified sets, then it's basically this non-interactive version that we just talked about. And from this, we can then produce preprocessing for arbitrary Q2 access structures. Okay, but we need a special type of linear secret sharing scheme, and that's what's called a multiplicative linear secret sharing scheme. Now, luckily, every multiplicative linear secret sharing scheme is Q2, okay? And if we had a Q2 linear secret sharing scheme which wasn't multiplicative, we can actually turn it into a multiplicative secret sharing scheme relatively easily for the same access structure. So basically, if you were given a linear secret sharing scheme which represented a Q2 access structure, then you can turn it into a multiplicative one representing the same Q2 access structure with just a small blow up of the linear secret sharing scheme. So it turns out that for small values of n and t, most Q2 linear secret sharing schemes you write down end up being multiplicative to start with, but if it's not multiplicative, you can extend it. So what does multiplicative linear secret sharing scheme mean? Well, to define that, what we have to do is define what we mean by the Schur product. Okay, so what is the Schur product of a secret sharing scheme? Okay, so in a secret sharing scheme we have these parties hold shares. Now in Shamir, each party holds one share, but in general, the parties can hold a multitude of shares. They can hold, 1, 2, 3, or 4 shares. Imagine replicated. In a replicated 3-1 scheme, everybody holds 2 shares. So the Schur product of the shares that you hold, of my shares Si and for secret S, my shares Si dashed for the secret S dashed, is basically the local tensor product of all the shares, which is, if I start with n shares per value, then the Schur product of my shares is a vector of length n times n plus 1 over 2. Now in Shamir, that just means I've only got one value, so I just multiply them together. Okay, so this is kind of easy for Shamir, but in general, it involves a little bit extra. Now, a multiplicative secret sharing scheme is one for which if you have a sharing of S and a sharing of S dashed, then you can express S times S dashed as a linear sum of all the Schur products. So you can basically express the product of the sharings as a linear combination of the Schur products of the local sharings. Okay? So this is what we mean by a multiplicative secret sharing scheme. Okay, so what happens? Okay, so we have that if t is less than n over 2, then Shamir is multiplicative. Okay, remember, if t is less than n over 2, then Shamir is Q2. Okay, that's nice. But if t is less than n over t, then Shamir is multiplicative. Okay, so why is this true? Okay, so if we have a sharing of S given by a polynomial f of degree t, and we have a sharing S dashed we have a sharing of S dashed given by a polynomial f dashed of degree t, then the Schur product is actually given by the evaluation of the product polynomial f times f dashed at the value I, which kind of means that S times S dashed is secret shared by a polynomial g of degree 2t. And these shares are given by the gi, which is exactly the same as fi times gi. F of I times f dashed of I, sorry. And since 2t is less than n, we can do the Lagrange coefficients for interpolation of a degree 2t polynomial allow us to express S times S dash is a linear combination of the GI. Okay, so in summary, the sharing of the product is given by a polynomial of degree 2t. Because 2t is less than n, we can do Lagrange interpolation on that polynomial g to express the product as a linear combination of the GI. So Shamir is multiplicative. The replicated scheme we had for the 1-3 secret sharing scheme is also multiplicative. Let's recall this. Each sharing S was given as the sum, each value S that we shared was given as K1 plus K2 plus K3, where party 1 holds K2 and K3, party 2 holds K1 and K3, party 3 holds K1 and K2. And then it's kind of easy to see that S times S dashed is just given by this product. And if we rearrange terms, we see that we've got this term here, which is a subset of, which is a linear combination of the subset of the Schur product held by party 1, plus this term, which is a linear combination of the subset of a subset of the Schur product held by party 2, plus this term here, which is a subset, which is a linear combination of a subset of the parties held by party 3. Having worked out or explained what a multiplicative secret sharing scheme is, in the next subset of these lecture notes, what we're going to do is explain how we can use the fact that we've got a multiplicative secret sharing scheme to define a protocol which will produce random sharings of a product. And that's what we're going to do, how we're going to be able to do multiplication of shares. So that's what we're going to do next time, but for now we've just covered what is a multiplicative secret sharing scheme. Hope you enjoyed it. See you next time.